Welcome to Ask and Learn.
In this problem, we have liquid water experiencing a process from one state to another. We wish to calculate the internal energy and the enthalpy changes under different assumptions. So for the first assumption in part A, we'll use the properties from the compressed liquids table. And in our compressed liquids table, the internal energy of state 1, which is U1, is equal to UF. Remember, this is at 50 degrees Fahrenheit, and this is 18.07 BTU per pound mass. The enthalpy of state 1, H1, at 50 degrees Fahrenheit is HF, actually plus VF into P minus P saturated temperature, and that's also at 50 degrees Fahrenheit. So these from our table are 18.07, that's BTU per pound, plus VF at this temperature is 0.01602. That's the specific volume, which is cubic feet per pound, multiplied by 50 psi minus 0.17812 psi. And we'll convert that to BTU. So this value for H1, the enthalpy of state 1, becomes 18.21 BTU per pound. Now the pressure of state 2, P2, is equal to 2000 psi, absolute. And the temperature of state 2 is 100 degrees Fahrenheit. So we go from 50 degrees Fahrenheit to 100 degrees Fahrenheit. Using our tables again, this corresponds to an internal energy U2 of 67.36. Again, that's BTU per pound. And an enthalpy, H2, which is equal to 73.3 BTU per pound. And so now we can find the change in internal energy using this method. Delta U is equal to U2 minus U1, and that's 67.36 minus 18.07. And we get the change in internal energy to be 49.29 BTU per pound. The change in enthalpy, delta H, is equal to H2 minus H1. And this is 73.3 minus 18.21. Hence we get delta H to be 55.08, also in BTU per pound mass. Now for part B, we are going to do the same calculation, but we are going to use the incompressible substance approximation. And this time we're going to turn to table 4 and find the values for the internal energy in state 1, U1, is equal to UF at 50 degrees Fahrenheit. And this is 18.07 BTU per pound. The final internal energy U2 is equal to UF, and that's at 50 degrees Fahrenheit. This is UF at 100 degrees Fahrenheit, and this is 68.03 BTU per pound. So you can see U1 and U2 here. So now we can find H1, the enthalpy of state 1, is HF. Again, this is at 50 degrees Fahrenheit, and this is 68.03 BTU per pound mass. And finally, H1 is actually not 68.3, but 18.07. And H2, which is the enthalpy at 100 degrees Fahrenheit, is 68.03. So what we can see is that U1 and H1 are the same, and U2 and H2 are the same from our tables. So therefore, the change delta U is equal to this change in delta H. The two changes are the same, and that's 68.03 BTU per pound minus 18.07 BTU per pound, and hence we get this change in internal energy and change in enthalpy to be 49.96 BTU per pound mass. So that's using the incompressible substance approximation. Now finally, for part C, we'll use specific heats. And using specific heats, we'll take the specific heat of water to be 1 BTU per pound R. So in this case as well, delta H is equal to delta U, as in the case above. And this is simply C delta T, where C is the specific heat and delta T is the change in temperature. So C for water, we said, is 1 BTU per pound R, and the change in temperature delta T is 100 minus 50 R. So what we are left with is the change in enthalpy, which is the same as the change in internal energy, is 50 BTU per pound.